Hi, everyone. Welcome to the Institute for Catastrophic Loss Reduction's Friday Forum for September 9th, 2022. I'm your host, Dr. Keith Porter. I'm Chief Engineer at ICLR. This is one in a monthly webinar hosted by ICLR, Canada's leading source for disaster resilience knowledge. Each month, we present recently completed research related to ICLR's mission to make Canada more disaster resilient. This month, it's unusual, we have two Friday Fora, one this week and one next. Next week, two Western University researchers, Drs. Greg Kopp and Julian Brimlow of Western's Northern Hail Project, will offer lessons on this year's record-breaking hail season in Western Alberta. But today, our esteemed colleague, Dr. Jen Beverly, will talk about the alarming growth in wildfire risk. She'll explain some mitigation and planning options. She'll brief us on new methods to describe a community's exposure to hazardous fuels and how to map the paths that wildfires can follow into the built environment. Dr. Beverly is a scholar and a professional. She serves as assistant professor at the University of Alberta and has worked as a research scientist with the Canadian Forest Service, and before that as a fire ranger. You can find out more about her in the notice of this webinar. Here's our agenda. Our webinar will last 90 minutes today. In a moment, our speaker will present for about half that time. Then I'll moderate Q&A for the rest of the time. Please feel free to chat your questions into the Q&A box. I'll try to pose your questions to the speaker in the order that they appeared in the Q&A box. If we have a lot of questions, I may only pose your first question, then move on to others, then circle back to additional questions that you may have asked. Our webinar is recorded, and ICLR is going to post a link to today's talk on Monday or so. So if you have colleagues who couldn't attend, let them know. Dr. Beverly, thank you so much for speaking with us today. Over to you.
Thanks for that introduction. It's really great to be here. I see some names that I know there among attendees. Most of you, though, I've never met, so it's great to connect here. And I'm going to talk for around 45 minutes. And the first part of my talk, I'm going to provide you with some background. I know some of you are familiar with this stuff, but the vast majority, I think, of participants today probably don't have a really strong background in wildfires. So I'm going to cover some basics, and then I'm going to get into some really exciting new work that we're doing right now, and we'll be publishing soon, that I'm really excited to share with you. But what I'm really thrilled about is that I get to have some discussion with you as well. So I'm hoping that we're going to have lots of time at the end. And as I'm going through my slides, in particular, if you see stuff that just is not making sense to you, take note of that, and let's come back to it in the discussion, because one of the things we're struggling with is how best to translate and communicate the analyses we're doing to make it digestible to people who aren't experts in wildfire. So your feedback is going to be really, really helpful in that regard. I'm going to turn off my video while I'm speaking, just to save some bandwidth, and then I'll turn it back on at the end. All right, so I'm going to talk about some fire pathway mapping, and it's some exciting work that we're doing. It's work that actually was funded by the ICLR initially, and we're continuing it on with some funding that we have from the National Research Council. So you're going to see some results from that. But let's step back for a minute and go over some historical context around wildfires and how they impact communities in Canada. So a number of years ago, I did a study when I was working at the Canadian Forest Service on documenting wildfire evacuations in Canada. I started this study in probably 2005 or so, wrapped it up a few years later, and we published it in 2011. So this is over 10 years ago. But at the time, we had documented 547 evacuation events. Among those events, there was documentation of just 497 homes having been destroyed, and just over 200,000 evacuees over that time period. The median number of evacuees per year was just around 3,600 people. The median number of homes lost per year due to wildfire was 2. These fires tended to come fairly close to communities. And there was only one civilian fatality that I was able to find confirmed documentation of. Now, more people have been evacuated since 2011, and in particular between 2011 and 2018, than in those previous 31 years. So the timing of the study was really at a transition point. In the years since, there's just been a lot more people impacted. There's been a lot of significant, devastating fires with significant home losses. And I've been watching these in the years since we published the evacuation study. One of them happened in the time frame that the study included. So Kelowna in 2003, we had 239 homes were lost. Then Slave Lake, which was the year I published the evacuation study, 433 homes destroyed. Fort McMurray, of course, I'm sure you're all familiar with that one, back in 2016. And then, again, we had some pretty devastating fires in recent years in BC, and of course the Lytton fire, in which really most of the village was destroyed. As these events are happening and time is passing, I have to ask myself, is this an indication of a trend or outliers? Now, people love to put a trend line through evacuation numbers, and it's not really appropriate from a data perspective, because the fires are burning into large communities or small communities, and that's really based on the distribution of the population. The fact that the fire burned in Fort McMurray in 2016 instead of a smaller community like Swan Hills, for example, in Alberta, means a substantive difference in the number of evacuees. But is this telling us that things are really changing, or is it just some randomness in there? Well, one thing we know about all four of these particular events that I've thrown up is that they happen under really extreme conditions. And so this is the fire weather index. So it's just a numerical indicator, a relative rating that tells us how just strictly from weather, how receptive the fuels are, for example, to burning, and how intense they're going to burn based on how long we've gone without a lot of rain and how hot it's been, and so on. So these maps are produced for every day, and it's based on the Canadian Forest Fire Danger Rating System. And so these are the maps for the days where we had Kelowna, Slave Lake, Fort McMurray, and Lytton. And you can see large regions of entire provinces are in that really extreme state when these events happen. So these events tend not to happen under moderate conditions. Okay, so we know it's going to be hot and dry and windy, and it's likely after a period of drying. It might not be a drought, but it's definitely going to be very dry conditions, especially in the spring. It's occurring in that window when things dry out after snow has melted, but the vegetation hasn't greened up and leafed out yet. And the fuels are very receptive to burning under these extreme conditions. So remember that. Now let's just step back and look at sort of the process by which one of these events unfolds. So you've got to have the fuels that are available to burn, and those maps are showing you those red blobs. That's telling us the fuels there are very dry and they're available to burn. So I like to think of it as moisture basically encapsulates the fuels. So when you've had a lot of rain, it sort of serves the purpose of encapsulating the fuels in a big tank so that the fire can't get at them at all. When it's dry, the fuels are released and they're available to burn. So you've got to have fuels in that dry state. You need an ignition, and you also have to have wind blowing in the right direction. So you need an ignition, you've got to have those receptive fuels, and you've got to have the ignition happening in the receptive fuels with the wind blowing it towards a community or the built environment or a particular structure. Now, this is really a perfect storm. So the perfect storm is when you've got this confluence of many factors or events, and alone, no one is particularly devastating, but when they're combined, you get this rare and devastating outcome. You could also call these a gray swan. So we know these events can happen, but we don't really know the likelihood, and we can specify the outcomes. So if this happens, this home is going to burn. But we can't really specify the probabilities because we're in a state of incomplete knowledge. And when you have events like gray swans, you can't really assign any probabilities to this. Any attempt to assign probabilities are considered, it's not rational, it's not science-based to do it, because it's so stochastic and because it is so difficult to characterize. You got to have the fuels in the right place, an ignition in the right place, in the fuels are available, and the wind's got to be blowing the right way, and you've got to have that value or asset or the built environment, maybe it's critical infrastructure, it's all got to be aligned perfectly for it to unfold. And so when you think back to those example fires that I had highlighted, and then I made the point, okay, so we had those things all aligned for the Fort McMurray fire. You could, on that day, the map for most of Alberta was a big blob of red. So this could have unfolded in a different location. The ignition could have happened somewhere else. It could have been aligned with a wind direction towards a different community. It could have happened that day the fuels were available. The fact that it played out where it did is based on this very stochastic confluence of factors. The ignition happened outside of Fort McMurray. It happened in a place where the fuels were available, and you had the wind blowing the right way. And so it unfolds that way. You can go back and look at them after the fact and say, well, this was predictable, but it really wasn't. It could have happened again. It could have been Swan Hills and not Fort McMurray. And if it had happened in outside of Swan Hills, you got that ignition aligned with the wind, pointing it towards the community of Swan Hills, there would have been a couple of thousand people evacuated, not 90,000 people. It would have been not that $9 billion event that played out. Okay, so let's just shift gears and talk about some basics about fuels and that availability of fuels and why it matters. And, if you've ever made a campfire, you already know the basics of this stuff. And you know what makes a good campfire. You know what you have to put together to have a successful campfire, to light a fire. You've got to have fuels of different sizes, and you've got to arrange them in just the right way in order to get the fire started. And if you take that campfire structure that you built right before you ignite it, and you go and spread the fuel out, the fire is probably not going to go, or it'll be, you might get it started and it's going to go out. That arrangement of the fuels, how close the fuel elements are to each other, this is really foundational to how fires burn. And so in the science of fire behavior science, we're really just building off that same stuff in terms of characterizing different fuel architectures that are of concern. And so some of the main things to think about when we're looking at, do you have hazardous fuels that can support the kind of fire that's going to destroy homes and structures? Should it happen close to a community? We're looking at, well, what type of fuel is it? We know leafy fuels like aspen, deciduous tree species don't burn as well. And they can burn, but once the leaves have greened up, there's a lot of moisture there, so you don't tend to get extreme fire behavior in those stand types. Whereas in conifer species, spruce and pine, that's where you can get some extreme fire behavior. But if you space out tree crowns, you're going to reduce that. And obviously it depends on the amount of fire. Just like your campfire, if you have tons of fuel, you're going to get a bigger fire. If you reduce the amount of fuel that you've got, you're going to have a smaller fire. So when we look at forests and we try to understand what fuels are hazardous in terms of having that gray swan event unfold, we're looking at the structures of the fuel elements and also the types of tree species. So these ones that I've highlighted here, they're what are generally recognized as the fuel hazard. When you're talking about wildfire, they're the potential source of harm. And I think this is the only equation I'm going to show you. But the one thing I want to highlight is that when we understand the fuel structure and how those fuels burn, we can identify the fuels that can produce high intensity fires versus lower intensity fires. And there's that intensity value, the kilowatts per meter. That's the intensity of the fire at the fire front. That's telling us whether or not we can suppress the fire or not. Because if it's below around 2,000 kilowatts per meter, generally you can have ground crews suppressing the fire. The kind of fires that burn into communities and destroy homes are the ones at the higher end here, 4,000 to 10,000 kilowatts per meter or higher. They're happening under those really extreme conditions. So for many decades now, people have taken those fundamentals that I've just walked you through and tried to produce maps to strategically plan for and mitigate these potential gray swan type events. Okay, and so there's been a lot of research, decades of research that have gone into producing basically maps for the most part that can help us understand where we can expect fires. And those maps and analyses tend to incorporate two, so if I had to split it into two groups, two kinds of information. There's things that we can know for today and maybe the next several days, but they're highly variable, say over the whole fire season. And that's something like how dry the fuels are. We know that's going to change as it rains, depending on the stretches of continuous days with little or no rain. Things are going to dry out. And the other thing is wind speed and direction. I can't tell you what the wind speed and direction is going to be at a location in 3 months from now. Those are things that you really can't predict with maybe over the next day or two, you might be able to predict it, maybe 3 to 4 days, depending on the weather patterns. But generally, you can't really predict that, what it's going to be. And same with ignition agents. Those are highly variable. They're what we call stochastic elements. And it's really difficult to predict. You can look at past patterns of ignitions for both people and lightning sources of fires. But those patterns, a lot of it's quite random. And even within the places where people do start fires, just because a person hasn't started a fire there historically doesn't mean it can't happen tomorrow, right? So you can look at historical data, but it may not give you the full picture. So that's the stuff on the left side of the slide. They're variable, they change. And there's a lot of predictive uncertainty. So when I say we can't predict things, it's really around this stuff over, it's going to change day to day. And I can't really tell you, July 7th, 2023, what the fuel moisture or the wind speed and direction or the possible ignitions are going to be on that day. I can't tell you that today, right? And I probably can't tell you that in May of 2023, right? I will know it. I will be able to predict it probably better a few days beforehand, and that's about the best I can do. Now, on the other side of the slide, there's the things that we can know for this season, probably over the next few months or even maybe the next couple of seasons. We know what burns, and I walked you through that in terms of the kinds of fuel that burns and the kinds of fuel that doesn't. We know what burns, and generally we know where it is fairly well. It's mapped. And we also know where the values are. So the houses and the built environment and the critical infrastructure. So these are things that, I can tell you on August 23rd next year or July 7th, 2023, or whatever date you want to pick next year. I can tell you at a location fairly well what the fuel is, what's been identified as fuel at that location, and where the values are. And you can also look at operational capabilities to get to that location and work there. So maybe accessibility to water, and the speed with which suppression resources can get to that location. So these are things that I can assess and know for a longer time period. I can know it for the next season or several seasons, for example, and I know it with a lot of certainty. Okay, so I don't, it's not going to, what the tree species at a location is not going to suddenly change tomorrow. Now, if there's a disturbance like a fire, that will transform it to a different state. But as long as there's no major disturbance, if it's a spruce stand that's there today, it's going to be there tomorrow. And I know that with certainty. Okay. So when people started making these maps, and I go back to like the 90s, and there was this threat rating model that some agencies in Canada today are still using, and it's a common approach. And the initial work to try to make maps, just strategically identify where you have the highest concern in terms of threats or risk or hazard. Those initial efforts, and this is the threat rating system that Brad Hawks and Judy Beck put out in the late 90s. This was really focused on those fixed parts of the problem, right? The things that had a fair bit of certainty. The stuff on the right side of that previous slide I just showed you. So what they started looking at was these overlays where they looked at ignition patterns over sort of a coarse area. They looked at the potential fire behavior based on fuel type and an assumption about an extreme weather condition. Again, they knew where the values were, so they looked at the values, and they could estimate suppression capability based on things like how fast they could respond or water availability. And so they could put together this stacked overlay of these different variables that they were looking at, but these tended to be the ones they were most certain about. There wasn't an attempt to try to incorporate into these threat assessments things that were highly variable or stochastic, okay? So then things started to change, and there's sort of a recognition that if you go and do that threat assessment approach, and you do an assessment for point A, which is on an island, and point B, you could get the same assessment value, even though we know that if you're on an island and surrounded by water, it's going to be hard for fire to get to you. So one of the main things that people started to tackle was, well, these point estimates of threat from these first attempts to do these strategic assessment maps, they're really detached from a spatial context. So they're detached from what's going on with their neighbors, basically. And they were ignoring that contagious nature of fire spread. So these are some good points, right? And so the solution at the time that kind of came up in the late 90s and early 2000s was, well, we'll use fire growth models and we'll spread fires to make these maps instead. So there was kind of a shift away, certainly on the research side, in terms of developing tools for practitioners to understand where can you expect fires and where's the highest concern areas. Let's start growing fires with models. And that was around the time where computational capacity, computers could do things that 10 years before wasn't possible on a desktop. You had spatial information data that you could work with to represent landscapes in a way you'd never had before. And I remember this. I was a student working as a fire graduate student at the time. So I was there and saw this shift unfold and this real excitement around growing fires in very complex ways in computers, and that this was going to help us really better understand where you could expect fires to happen. And I used to show this slide with the arrows here in the top corner when I was doing presentations back, 2003, 2004. I'd be like, yeah, if you simulate the spread of a fire, you can bring that neighborhood, that surroundings back to the point, right? So it was giving you spatial context. And this was this really important shift in how we were assessing fire risk. We could use these simulation models. And the fire behavior prediction system, which is used in Canada and has been around since the early 90s, had equations that could be used in these computer simulation models. Now, the underlying equations are really, really simple, and they're based on really small numbers of data. So these graphs on the right are just showing you those data points that were used to build the equations that were then embedded within these computer models. A lot of people today who use these models may not be aware of that those equations, some of them are based on like 50 fires that were observed. And they drew a line through the data points. I mean, it's a very powerful tool, but it's based on 50 data points from that were collected on fires that were observed many decades ago, and those equations were then embedded within these new fancy models. And so the lower picture there on the lower left is showing you what one of those simulations look like, and you have this very powerful spatial representation of how the fire is going to spread from point to point. Basically, though, using those really simple equations, that were formed from a small number of observations of fires many, many decades ago. But the power of these simulations, I mean, I started using this Prometheus fire growth model, which is sort of that image in the lower left is showing you an output of a spread. The first time I ran that was in 2003, so almost 20 years ago. It's been around for a long time now. Not long after it was developed, so in the early 2000s, the next thing people said is, oh, well, let's start simulating lots and lots of fires using a Monte Carlo process, and then we'll just throw ignitions down on a landscape. We'll grow the fires, and using those basic equations in that Prometheus fire growth model, we'll grow the fires in our representation of the landscape in a computer. We'll wipe it clear, and then we'll do it again, and we'll grow more fires with simulations. So again, this was taking a one fire simulation and now doing lots and lots of fire simulations. And this became an exciting new way to try to understand where can you expect fires to burn. So to create those risk maps, those maps of hot spots of where you should focus your efforts for mitigation or planning. So you grow the fires, and again you wipe it through. And so to calculate a hotspot map, basically they would just take these 2 iterations, but in reality you wouldn't just do 2 iterations, you would do 25,000 iterations. You would grow all these fires, and then you would calculate a burn probability at a given pixel in your landscape. So you would just say, go look at a little area, see how many times that pixel burned, given the number of chances it had to burn in your simulation world. And then that's used to calculate your burn probability at that location. So if you ran 2 iterations, that pixel had 2 chances to burn, it burned 1 out of 2 times. So you could then calculate a probability. So this became sort of the dominant approach to trying to produce these useful maps to help understand where you have these risk hotspots or threat hotspots, whatever terms you want to use on your landscape. And so if you look at the next pixel near it, that one burned twice, and so it would have a burn probability of 1. But as I said, this is just for you to understand the concepts around this. Whenever if you should encounter someone who's showing you a burn probability map based on simulations of wildfires, this is how it was built, right? It was, you run some simulations of fires, you look at how often locations burn. And embedded within these models are simple equations that are part of the forest fire behavior prediction system developed in Canada. So I started using these approaches, back in about 2004, when a model called Burn P3 was released by the federal government. I was a federal government employee, I started using it. And the initial thing that I encountered was that I couldn't replicate my maps. And as a researcher, of course, that's kind of a key thing when you're doing any kind of modeling. If you do a simulation, you produce a model result. If you were to just duplicate it with all the same steps and data and processes, you should get the same result. And the problem was that this approach was not producing maps that you could replicate. Now, these 2 maps I'm showing you they're actual examples of an attempt to replicate maps. And you can see they're somewhat the same, like in terms of general patterns, but you can zoom in on areas that within the maps, and you can see that, that you're kind of getting a different result. And so I was trying to understand why it wasn't working and why I couldn't replicate maps, because I could run the simulations twice and I would get maps that were 30% different at the end. And so which map is right? Because if you want to give a map like this to a decision maker, a practitioner, operational staff, and say the dark parts of the map burn the most when we simulate things, and so the dark parts of the map are where you should focus your efforts for, say, managing the problem, doing vegetation management, removing some of the fuel, or taking other actions to protect communities that might be nearby those dark areas. You would hope that you're giving them a map that's right and stable, and you can reproduce it. I was extremely concerned that we were potentially going to start giving out maps that we couldn't replicate. And I started to try to solve it by doing more and more iterations. And so at the time, the researchers who developed the model were saying run around 500 iterations. And I started running 20,000 iterations, 25,000 iterations. I was growing 100,000 fires, trying to find out if you grew more fires, if you did it more simulations, would the maps stabilize and could they be replicated? And I never got that close to it. To my knowledge, that problem still hasn't been solved. Nonetheless, I was using the model, and I published a study back in 2009 of a burn probability map produced with those methods I just showed you for a pretty big area in West Central Alberta, about 2.4 million hectares. And within my study area was the community of Slave Lake, as well as Swan Hills that I mentioned earlier, Fox Creek and Whitecourt. And there were other places as well, but those were sort of the main communities we were looking at. So you can see that, you know, the map has some dark red areas, and when we ran simulations, those are the areas that burned most often, right? And so the idea is that you produce maps like this to help inform mitigations and contingency planning for these communities or for other values within the study area. So, you know, when I did the study and the results were actually finished, this map was actually produced using 2005 data. The study wrapped up in 2007, took a couple of years to get it out there. The publication process is kind of slow. So it comes out in 2009. Well, of course, 2 years later, in 2011, Slave Lake encountered a fire. A fire burned into that community. And so I immediately went back to my map and I kind of wondered, well, you know, was this map a useful assessment for informing risk management priorities? And you have to reconcile that if you're looking at this map, there's really nothing about it that would have pointed me to Slave Lake as a priority, right? I would have focused probably on Swan Hills. If I had to identify priority areas, it would have been those that coincided with the red spots of the map. So I started to be concerned about this and go back and say, well, you know, I produced that map using 2005 data, so I can go back and overlay fires. And I did that. And I started showing these results, probably 2016, so quite a while ago. I was showing these to people. You know, I was kind of concerned that many of the fires don't overlap with the hotspots on these maps. And so this graph here on the right is just showing you, if I took all the burned area that happened after I made the map, where those burned areas coincided with. And most of the burned area is in the moderate or low or very low burn probability classes in the map. There's very little area burned that actually happened in the dark red spots that you would tend to focus on if you were thinking that map is a way to help me identify the places where I want to take action. So obviously, yeah, I was really concerned about that. And, you know, I started talking to other people using the models. Neil McLaughlin, Alberta Wildfire had been using it to inform strategic planning in the province. So that Burn P3 model, which was produced and marketed by the Canadian Forest Service for strategic planning purposes, was being used by agencies. And so there were other people making maps with that model, and Neil was one of them. So he started overlaying his burn probability maps with the subsequent fires that happened, and he found the exact same results. And so a couple of years ago, we published a study where we took all of our study areas and we went in there, overlaid the fires that happened after we made the maps. We're basically trying to validate these assessments, okay? We're trying to say, does this work? Are these maps helpful if you're a decision maker and you're looking at these risk assessments and you're making decisions based on them? Are they helpful? And what we found consistently was that 70% of burned areas were happening in locations where burn probability was in the lower half of the range. So the cold spots on the map. And so here's the two examples that I've talked about earlier. So Slave Lake, you can see in the background the pre-fire burn probability map. The red areas within the community are the locations that were destroyed by fire. So those are residences that were destroyed, predominantly residences were destroyed by fire. And you can see that, yeah, the area adjacent to those destroyed structures, it had sort of mid-range burn probability. Fort McMurray, this is the burn probability map produced with simulations prior to the fire. So this map was made in 2016 before the fire. And then obviously the fire came through, and there's nothing alarming about this burn probability map that might lead you to believe that this is a priority area to focus your efforts. And so, this is something that we had to try to reconcile. Both Neil and I, obviously, we had been, at the time thinking these are really wonderful approaches. We both spent, as analysts and as modelers, we mapped with these models because we thought that they would be useful to decision makers. Part of being a modeler, though, is you've got to check and see how your model works, compare it to the reality. And so that's the step that we did. And we're surprised. But ultimately, when you think about it, and I'll explain why, it's not surprising. The reason, let me go back to this, the reason you don't see good alignment is sort of relates to what I was talking about in my initial few slides. I was talking about that gray swan perfect storm condition. I was talking about how when you have a lot of variability and stochasticity in the process, ignitions are stochastic. I can't predict them very well at all, where they're going to play out. And wind direction is another thing. It's really stochastic. It's variable. So when your process that you're modeling has a lot of that stochasticity, right, and you're trying to predict those perfect storm events, it's actually not rational to try to use that probabilistic approach. It's not, there is no scientific basis for doing it. When we simulate all those fires, what we're doing is simulating all of that stochasticity. So we're taking the things that we do know, which is the fuels. We know with certainty where the fuels are. And we're throwing ignitions down, growing all of these fires from different locations and different winds, and we're seeing what burns, but we have to simulate so many of those fires in order to replicate the maps for it to kind of stabilize, that what we end up doing is then trying to mute out all of the stochasticity. You can think of it as I'm taking something that I know, which is where the fuels are, and I'm overlaying all of this stochastic confusion. And ultimately, that's why we end up with these maps that don't work. So that's why the probabilistic approach doesn't work well, even though it sounds fabulous and everybody's doing it. I mean, every other week, somebody sends me a manuscript to review around a probabilistic approach based on simulations. And I think, okay, it's really fun to do this modeling. If you're a modeler, it's lots of data, it's lots of complexity, but it doesn't work. And so this is something we have to reconcile. Okay, so when we got these results, I had to start rethinking, well, then how do we assess this stuff with in any kind of a reliable way? And I went back to some work I'd done in 2010, which is an exposure assessment process. And this process ignores all of the stochastic pieces of the problem. So I'm not concerned about where the ignitions are happening. I'm not concerned about what weather the fire is burning on under. I'm not trying to simulate at all. I'm just looking at a location and saying, am I exposed to possible ignition based on what's around me? And it was an attempt to focus on that one part of the process that we know for certainty, or we know with a great degree of certainty, which is the fuels. We know what burns, we know where it is, and we know where the values are. So let's focus on the things that we know. So these exposure assessments were done for communities, and we were doing them at a 30-meter, 100-meter, and 500-meter radius to say, hey, if you're standing at a house or a location on your landscape, you look out around you 30 meters, are there fuels, hazardous fuels within that window that can transmit fire to you? Because if there are fuels there that it's possible for them to transmit fire to you, you are exposed to a possible ignition. And we did this for radiant heat exposure, short range embers, and long range embers. And I had also published that back in, I think 2010 for the community of Slave Lake. So this is the pre-fire assessment of exposure before a fire burned into the community. And so this is the zoomed in part of town. The red boxes are showing the structures that burned. And the shadow here is showing you the perimeter of the fire that burned in. And so we had mapped these exposure areas before the fire, and they, it's one data point, but when we went back and looked, we thought, well, there's fairly good alignment. The fire happened to enter the community along a place of significant exposure. So I thought, well, let's just do this at the landscape scale, because we know it works, and we know we need an alternative to burn probability maps that don't work. And we know focusing on fuels seems to be a good way to go because there's certainty there. So let's do it. And so myself, Neil McLaughlin, and Elizabeth Chapman, both Neil and Elizabeth at the Alberta Wildfire, the provincial agency responsible for fire management here in Alberta, we ran an exposure assessment across the whole province. And so we just did a simplified version of it because the fuels are kind of coarse. We just looked out 500 meters from every point within the forest protection area and said, is that point exposed to possible ignition? And so you just take the fuels and you've got a point that you want to assess. And so there's 80 pixels within that window. And I'm just asking how many of those pixels can transmit fire to my white cell. And I can just map the hazard fuels. It's just a binary map. And then I count up how many hazard fuels are in my exposure window, and I can get an assessment of how exposed I am. The maximum exposure would be 100%. In this case, most of the area, I've got 75 out of 80 pixels have hazardous fuels, and so the exposure is 0.94, 94% exposure. So it's a real simple approach to try to understand if fire can transmit to a location. But we subjected it to the same test. We overlaid fires. And we checked to see if these red spots on the map, the high exposure areas, aligned with the fires. And remarkably, we absolutely saw that. This is a univariate one variable model. It's a one variable assessment. It's based solely on fuels, but most of the area burned. And so these gray bars are showing you the burned areas, and you can see most of the burned areas happened in locations with exposure 60% or more. And so I'll just quickly skip over this because it gets a little too detailed, but we looked at making it more complicated because when we tried to publish this, the reviewers immediately said, it's too simple. Can you make it more complicated? And so we tried making it more complicated, looking at things like intensity, some of the things I've alluded to earlier, the crown fuel load, rate of spread, and weighting pixels based on some of these other variables, and none of that improved performance. And so we just stuck with a simple exposure assessment. So we can produce these maps of exposure, and they're just based on fuels, but as conditions change day to day in terms of fuel moisture and other variables that are stochastic, ignitions, you can combine that information with your static exposure assessment day to day, because you have a better predictive ability about those variables, so you can incorporate them later on. Okay, so what are we doing now? That was a lot of background, but you needed to understand it to kind of understand the evolution of exposure assessment and why it works, and why it's an effective tool for decision makers. It's one of the few assessment, actually it may be the only one that I'm aware of, risk assessment tools that's been released in Canada that's actually been validated against real fires. Okay, so we checked to see if it works, and it does. Then we started saying, what else can we do with it? And so what we did next is, with some help from the ICLR, we developed some fire pathway approaches. So we wanted to use that basic exposure assessment to map the likely fire routes into communities. So again, we just start with the fuels. We run an exposure assessment and this is just a point on the landscape. It's just, it could be a value, it could be a community. You can pick any point. we run this exposure assessment. It's fast, it's easy. You can do it in an afternoon. You can rerun it next week if you need to. If the fuels change, you can rerun it next year. It doesn't cost much to do this. You don't need to make this map. You don't need fancy modelers. You just need somebody with basic GIS skills. So it's cost effective. It's easy. It's one variable. It's based on the fuels. We can make this map and we can plot a point on it. Any value, community, asset, infrastructure that you're concerned about, you can overlay railways, you can overlay roads, but let's just look at this one point. Now we know most burned areas are going to happen when in the darker red parts of the map. So let's just look at it as okay, the gray areas here are showing you where there is that 60% exposure. When we looked at real fires, we know most of the fires happen in these gray areas. Right. So if you're looking year to year and you're trying to identify what parts of your landscape you can expect fires, it's the gray areas on this map. That's where fires happen. And we can calculate that with exposure. It's just, these are the areas that had 60% exposure or more. So we decided that, well, let's look at the exposure in different directions. So if you're worried about fire coming into this community from this direction, I'm drawing the line out from the community, but you can see that that line doesn't overlap with a lot of the gray. The gray is where the fires happen. Now this line overlaps with a lot of the gray. So that trajectory into the community or out from the community, that's got a lot of continuous exposure along a directional trajectory, okay? So if you go and overlay transects into real fires, and so we did this, what you see is that those transects tend to happen in the gray areas. So this is just one example of a fire. We went in there and looked at hundreds of these. We put transects through the core areas of the fire. And what we found is that when we then checked to see, are those lines, those dotted lines, those transects, do they overlap with the gray areas, the high exposure areas? And for the most part, they do. You can see there can be instances where they don't perfectly overlap. So there's a part of this one line to the far right. You can see there's pink underneath there that's not shaded. And that means the transect doesn't overlap with the critical exposure area. The exposure was lower than 60% there. But most of the lines are overlapping with the gray areas. So it kind of validated for us that you can take this transect approach to try to understand vulnerability along a trajectory. Okay, and when we looked at many fires, we found this was consistent. So this graph is showing you of all of the sample transects that we looked at, and we looked at hundreds of them in historical fires, most of those lines, most of it, almost all of them have 90 to 100% of that line overlaps with the gray areas. So they fall in the gray zone of the map. There's a small number that don't, and that's because the fuels were misclassified or the line is just on the edge of the fuels because it's kind of a coarse map. But there's some cases where they don't, but almost all of the lines, almost the entire extent of those lines overlap. So we said, okay, we'll take those community locations or any kind of value or asset. You can take that location and you can draw 1 degree transects out in every possible 1 degree directional trajectory. And then we can calculate a graph like this on the right. So that is, if it's shaded, that's where you have that continuous gray underneath for the most part, right? So 80% of that line is continuous from 0 to 5 kilometers, 5 to 10, 10 to 15. So you can kind of see the shading underneath on the left, that when you go to the north, so that 0 is due north, and you go to the north towards 15 degrees, 30 degrees, 45 degrees, there's not that continuous gray. Whereas out to the due west, and to the south and southwest, you've got a lot of continuous gray. So we just use these trajectories to create this visualization and quantification of directional exposure. So I'm going from a fuel map on, so what I've just walked you through this whole presentation so far is how I get from a fuel map on the left to this simplified directional exposure dial graph. You can call it a radial graph, but it's showing you that particular point is exposed to these directions where it's shaded. And we can do this for every single community. And in fact, we ran this for 900 communities in Alberta. So we can identify which communities are exposed in which directions. And we can also sum it up for the province as a whole or for regions. So we could say this region is predominantly exposed from the southwest, or this region is predominantly exposed from the north, and so on. So there's been a fire in Jasper in the last couple of weeks. You may have heard about it. This is the exposure directional pathway map for Jasper that we just ran. And if we overlay it on the town, you can see there is a directional exposure to the north. So if that fire does move in to within that 15-kilometer boundary, it will have a direct path into town. Now it's a fairly narrow path, but you can see for a community like Jasper, the predominant exposure is out as a fire coming in from the west, but there is that one path from the north. So what we're hoping with this exposure work is that we can put these simple maps and both the landscape level one and the directional one in the hands of practitioners, managers that have to make decisions about priorities, where you're going to focus your effort. And we can also combine it with information about wind directions historically. We can, but I see it more as a useful tool for day-to-day management, where on a given day, if you've got winds, for example, for Jasper out of the west, so it's going to blow a fire into the community from the west, and you happen to get ignitions within that exposure pathway, they need to be prioritized for suppression. And those would also be the directions that you want to prioritize for mitigation, fuel management. We've been working with these maps to look at things like egress routes for evacuation. So we just finished a study. I did it in collaboration with Dr. Amy Kim at University of British Columbia, and our student who's just defended their thesis. So you'll see that work come out soon. But we've looked at how egress routes overlap with these pathways. So if you have only one route out of a town and it happens to be within your key exposure pathway for fire to come into town, a fire could potentially encroach on the community and block your own egress route. In other communities, you could have a situation where fire has a pathway in from one direction and it might only cut off one route. It's going to force evacuation to be limited to your other egress routes. And so we were looking at the time it would take for people to evacuate, for example, given what's left if a fire comes in from a specific direction. So there's lots of other applications outside of just evacuation planning, but for contingency planning around where to prioritize vegetation treatments and whatnot. Now, everything I've shown you so far today is a landscape, predominantly landscape level perspective. Where we see what we're working on right now is running these assessments at a much more localized scale. So I could do these graphs for looking at an extent of, say, 500 meters, but I need fine resolution data to do that. And so we've started doing that for some case study communities, and we'll have those assessments probably over the next year to see how these graphs look when you zoom in, because you could look at an individual structure and you could look at 500 meters around it and look at the directional vulnerability of that specific structure as well. So we think this is going to be a really neat tool that'll just add to the toolbox available to whether it's communities or individual homeowners, provincial agencies, for understanding directional vulnerabilities for wildfire. So thank you. I've thrown a lot at you and went over 45 minutes. So for those of you who were able to maintain your attention, I appreciate it. I'm really excited to hear any feedback you have on this work or any ideas about how we could make it easier to understand.
Thank you so much, Jen. We have several questions, and I'm going to give them to you one at a time. Michael Curry asks, after fire burns through an area, can the vegetation exposure be considered negligible and removed from exposure determination? Similarly, for fuel treated areas, can the vegetation exposure be considered negligible and removed from exposure determination, and for how long?
Yeah, great question. And I mean, the easy answer is yeah, for sure, because if a fire moves through an area, it's consuming the fuel and you end up with what we call a fuel limited condition. And some of my research, I looked at characterizing that with actual data from fires that there, and we were able to statistically analyzing real data show that when you have a fire, it has a protective effect for a period of time. Now that the second part of that question is the period of time, how long does it last? Great question. It depends on the ecosystem for sure. So we have just validated these exposure assessment metrics in Portugal. So I have a PhD student in Portugal and they ran the assessments on fuels in Portugal, and they got basically it performs just as well in Portugal as it does here in Canada, which is fantastic. But the difference is the fuels in Portugal can reburn like in 3 years. So the way we were analyzing it, we had to be aware that, yeah, 3 years later, you can have another fire here. In the kinds of ecosystems and forests that we have, certainly here in Alberta and across most of Canada, some fuel can reburn, like say grass fuel can reburn. But if you're looking at the forests where you have the most intense fires, they are going to have a protective effect probably anywhere from 20 to potentially 40 years or longer. The more extreme the weather condition, the shorter the protective effect. Because basically, if you have really extreme conditions, weather is going to override your fuels. And you've got 100-kilometer-an-hour winds. It's really hard to stop the fire by spreading the fuels out or limiting the fuels. It's going to burn. But under other conditions, more moderate conditions, you'll see that protection for sure.
Can I follow up on that? Raises an interesting question from my perspective as an engineer. What should we build and how should we build it? And it raises a question, I mean, 20 to 40 years is shorter than the average life of a new building. So as we build and consider what's the hazard to this particular new building, we need to look, it sounds like we need to look farther back than the last 20, 40 years, look farther back, at what was there, what were the fuels that were there 40 years ago, if there was a fire between now and then. And similarly, if there hasn't been a fire between, in the last few decades that would change that, is this sort of short-term, am I correct that the short-term protective action of a fire doesn't really have a meaning for what we build and how we build it, because our houses are going to last longer than that protective action?
Yeah, it's a good question. So I mean, like, we do the exposure assessment, so we can do it at the community scale and say, right, like today, this part of the community, maybe it's a new residential development, for example, is not in a high exposure zone. And so maybe there's this thought from the developers that it's not a concern area for how we build, what standard the houses are built to. Do you need to make them as fire resilient as possible when they're not exposed? But I think we can absolutely identify the areas that are maybe currently low exposure that have potential to be reforested, for example, right? But you're right, just because some low exposure areas might be low exposure because of the vegetation burned, like you said. So maybe in a place like Fort McMurray, Slave Lake, where you've had recent fires burn into the surroundings area, right? Other low exposure areas are because maybe there's water or non-fuel. In the Rockies, for example, you've got a lot of non-fuel, or you've got large water bodies, and that's never going to change. That exposure could be characterized in terms of potential future exposure too. I mean, you absolutely could characterize that so that you could identify this is low exposure that's robust, it's not going to change, versus this is low exposure that could potentially change depending on what happens with the vegetation around the town. Yeah.
Awesome, thanks. Martin Alexander says, thanks, Jen. What is the land or vegetation cover types for the less than 60% exposure? Water, rock, recent burn, road, etc.
Yeah, so when you go, let me see, let's flip back to some of the slides, might make it easy. Okay, so exposure, go back to an actual exposure map. So exposure is looking, again, it's just that window around the point, and it's saying, is there fuel that can transmit to me? And so that percentage, like if we go back even further to that, this diagram might be the most helpful. So when I'm calculating exposure for that white cell, I'm just saying, okay, I'm going to look out a distance around me. And I know that if it was all hazardous fuel, my exposure would then be 100%. I'm 100% exposed to surrounding pixels that can transmit to me. In this case, yeah, I'm showing you an example of a 500-meter window. There's 80 pixels and 75 of them can transmit to the white cell. And so we give it a value of a 0.94, 94% exposure, okay? So what's around it when it gets below 60% exposure could be a lot of different things. It could be, yeah, non-fuel. At the landscape scale, we consider deciduous stands as a non-hazard. So we're saying that that's, if I have an aspen stand, a fire might be able to spread through there, but can it generate embers to travel to this particular cell? We're saying no, it can't. So the exposure classification process does involve a decision about what you call a hazard fuel and a non-hazard fuel. But the approach seems to work and is robust. So it was validated independently by researchers in Alaska. They used it, they tested it, it worked just fine. And they're the ones that decided how to classify what the hazard was. And they tested against real fires and it matches. And then, like I said, we just did it in Portugal, totally different fuel complex. And I had nothing to do with the classification of the fuels because I don't know the fuels in Portugal. So local experts said, okay, this is a hazard, this is not. And did that binary classification, computed exposure the exact same way, and sure enough, it matches fires. And actually in Portugal, the threshold's more like 80% exposure. Almost all of the fire happened in areas with 80% exposure. In Alberta, the number we found was 60% exposure or more, that's where the fires were happening. So yeah, I mean, it's based on some subjective decision-making about the fuels for sure.
And I would imagine that Martin can find the particular choices that you made in the citation you've got at the top of the page here,
Yep.
right? All right, thanks. Next question, Michael, I'm going to skip over your second and third questions and come back to them later on. But our executive director, Paul Kovacs, compliments you. He says, Jen, wonderful presentation. Thank you. Please describe how a community can use your new approach to reduce the risk of fire damage in their community.
Yeah, that's a great question, Paul. I'll flip, see if I can flip down to the end. So yeah, so let's look at Jasper because it's happening right now. So how would a community use it? And I love that question because it's like, as a researcher, I think to me, it's like, well, it's obvious, isn't it? But yeah, let's talk about that. I'm working closely with a bunch of communities and I'm trying to better understand what they need from us. So I have a project that I'm working on right now with the Forest. It's funded by the Forest Resource Improvement Association of Alberta Fire Smart program. And it's really about, it's actually not a research project. It's a project that allows me to go and talk to communities and spend time on that. And so I've been touring around communities and talking to the fire chief and hanging out there. And I did that this summer. I was up to High Level and I was in White Court and I was in Rocky Mountain House in Nordig and talking with the local fire managers and fire chiefs who are trying to protect their communities in those zones. and listening to their perspective on what they're concerned about. They are in all of the places that I'm visiting for this project. It's places where they've done a lot of fuel management. So they are able to access grant programs, these communities. They then take that money and treat the fuels. And by treatment, I'm referring to a fire smart vegetation management treatment. So, I talked about, hey, you know a lot about fuels if you've ever made a campfire, right? You spread the fuel out and the fire goes out. And so that's really what fire smart vegetation management is. It's like change the architecture of the fuels, spread them out, separate the crowns, make more space between the ground and the crowns of the trees, the canopy. Take out some of the surface fuels, reduce the fuel. So all the fundamentals from from a campfire, it's just applying it to a forest stand, changing the architecture. There's limited money to do that. It's costly. You have to maintain it over time. And so that's some of the things that I know that these communities are grappling with. Like you could do a fuel treatment 10 years later, but things are growing back. So it's costly. Vegetation management is costly. They need to prioritize where to put it. So I think one of the key things about this analysis that's going to be informative is for positioning those types of treatments, knowing maybe, hey, like in the case of Jasper, you can see the continuous pathways predominantly from the west. A lot of this stuff is probably intuitively known to the people who know the areas, but this is a way to really quantify it. And then we can go and change the fuels and rerun it, and you can see the difference in the numbers. So it's kind of a way to standardize the common knowledge in some ways. And then it allows you to make comparisons between communities and over time. So for vegetation management, I think it could be informative. The other one, like I mentioned, we have already done a study looking at overlaying evacuation routes with our pathways to understand how those things are interacting. There's been some interesting work from the railways. Interesting if a railway can start a fire or a power line can start a fire, you could actually run this along those linear features to see where you have exposure to spread out from the source. So you could actually reverse it around and think of it as a starting place for a fire. Where can it go? So I think it's a really powerful tool for looking at most risk assessments, and there's tons of them out there. And like I said, somebody's coming up with a new risk assessment map. It's a threat assessment, or it's a burn probability map, or it's some simulation that they've done. And they're making these maps with hotspots. And they're almost, I've yet to see one that's not omnidirectional, which means they don't specify directions. They are omnidirectional maps. They haven't given you any information about the directions the fire is going to flow through the landscape. So this work, I think, is groundbreaking there. Like I've never seen anything that provides a simple, easily completed assessment of directional exposure to fire. Fires are going to come in from a direction. They always do. They're blown by wind. There's always a direction. And if you know what the winds are going to be tomorrow, this could be extremely powerful for protecting communities when you have fires going. So you have a going fire like Jasper that's 18 kilometers to the north of you, and you can see there is a pathway in. Same with triaging fires. If you've got 5 fires and you have resources to fight for, where are you going to put your resources? Well, if you've got 4 fires that don't have pathways anywhere, then maybe those are the priority. Maybe you want to throw everything at that one fire that's in, it's got a direct run into town. And so this is what we're hoping is that this kind of information is going to be informative at multiple scales for strategic planning, for responding to fires, for evacuations. Yeah, so maybe some of you can think of other applications as well.
Awesome, thanks. Our next question comes from an anonymous attendee who asks, how often do you think the maps and underlying data should be updated?
Yeah, so whenever the fuels change, and because it's so easy, like I said, I've already run this for all of our 900 communities in Alberta, and you can we developed this very simple approach that's still been validated. Like we made sure it worked. It's been validated against actual fires, but it's simple. if the fuels change, you need to update it. It doesn't cost much to rerun it. So if you had a lot of fire one year, so if you had a community where there's fires in the surrounding landscape, then you're going to want to update that fuel layer, redo the exposure assessment. Likewise, if you have other disturbances, harvesting, that kind of thing, that might change the fuels. So if the fuels are stable, you don't have to rerun it, and oftentimes they are. In the if you have a community that's expanding and there's new subdivisions, one of the communities I'm looking at, Nordig, when I met with the fire chiefs and the structural protection crews, they were showing me the new developments that are going to be built, and so we were looking at, okay, the community is expanding out in one direction, but fuel is being removed as they build out as well. So you've got to take that into account if the community is growing, for sure.
Okay. Next anonymous attendee asks several questions, and I'm sorry, attendee, I'm just going to ask relay your first one. With climate change, has the fire season lengthened? I was really surprised to see FMM and Slave Lake occur in early May when temperatures are normally cooler, and often you still have snow melt in that part of the world.
Yeah, it's a great question, and actually it touches on something that I didn't mention in my presentation, but that we're also working on, which is the other, what I've pushed for in my approach to the assessment process is that you decouple things. When you grow a fire, everything's wrapped up together, all the weather and the ignition and the fuels, it's all wrapped up into one fire outcome that you simulate. My approach, as you've seen, I'm breaking it out apart and focusing on what the fuels. What you're referring to, the weather, is also important. You're absolutely right. Fire seasons are getting longer. I haven't personally studied that, but other people have, and that's happening. The other thing that's happening is the length of the season is longer. During that time, you're getting more days when the disaster fires can happen, more of those extreme days. And I have studied that part of the problem. So I have looked at historical weather data myself in Alberta and said, okay, well, how many days in the season do we get the kind of conditions where you can have a fire burning under the extreme intensities? So I mentioned the Canadian Danger Rating System, and there's the Canadian Fire Weather Index System. So there's these indexes that give you an indication of how dry stuff is and how fast a fire, but it's just based on weather. So you might say, well, this is a day we can have a blow up fire, right? When I showed you those images of Kelowna and Slave Lake and Lytton and Fort McMurray and those big blobs of red on the map, that's the whole region is dry, and you could have an explosive fire pretty much anywhere in that region. So the question we were asking is, well, how often does that happen? Does that happen once a year? Does that happen 5 days a year? Does it happen 10 days a year? Could that play out? Could that gray swan play out? If you had the ignition, we know where the fuels are, but will you get the weather you need for it to happen? How often, what's the frequency of those events, of those days? And it varies regionally, right? So in some parts of Alberta, you don't get that many days where that can happen. It can happen, but it's a rarer occurrence. And so you can actually look at the historical data. Maybe you just go back 5 years because you want to capture global climate change. And you can characterize across a region, hey, in this location, I tend to get those days more frequently. And then you can overlay it with our exposure assessment. So for example, I could have lots of exposure on Vancouver Island. There's lots of fuel there, but you don't tend to get a lot of opportunities for those fuels to burn because it's too moist. And you don't get a lot of ignitions either, right? So incorporating the weather part of it is something we're working on as well. And we've had some good success in sort of how you summarize it so that you can say, well, here's two communities. They might have equal exposure, maybe equal amounts of pathways. One of them, though, has those kind of fire blow up days a lot more often. And so we're looking at a way to bring in that weather related information into these assessments.
Awesome, thanks. Cheryl Evans asks, do you do any future climate change scenario exposure assessments that consider future impacts for planning? Or is it too complex because the ecosystems continue patterns of succession?
Yeah, it's a great question, and it's something that I've had some really good conversations on proposed projects. We haven't done it yet, but ultimately, if you can model the future landscape, you can run a future exposure assessment. So if you have a climate change scenario and you're doing vegetation modeling, and you can say, well, this is what's going to happen to the landscape 20 years from now under climate change. And and there are vegetation modelers who do that kind of work. And so we could absolutely run an exposure assessment on their prediction of what the future landscape is going to look like. And I've had some good discussions about doing that actually for some study areas where there are some vegetation modelers doing that work. So they are predicting what the vegetation is going to be. And I can run an exposure assessment once they say, okay, this is going to be the predicted vegetation in 2050. And so we can run it. Now, in the paper that Neil and Liz and I published, we showed that when we compared the exposure map for the whole province in 2007 to the version in 2019. So we took the 2007 fuels and we ran an assessment. And then we took the more recent fuels, the 2019 fuels, and we ran an assessment. What we saw was even over that fairly short time period in recent years, there's been an intensification of exposure. So the high exposure areas where fires happened, we've got more of that land now than we had just 13 years ago, right? So that's on real data. That's not a projection. So we know that those exposure assessments are going to change over time as the fuels change. And so, yeah, you could absolutely run it for a scenario into the future.
Cool. Kulbhushan Joshi asks, who says, this is a great presentation as well as very impressive research due to its simplicity and usefulness. So thank you for that. How small or large can the pathway radii go while still being meaningful? Building level to county level?
That's a great question. I think absolutely building level. So you could run it on, like I was saying, you could go out 30 meters, 100 meters, 500 meters with you. The only requirement to do that at a very localized scale is you need fine resolution fuels. And that's actually what we're doing for a number of projects I'm working on now. We're mapping super fine resolution fuels, and we're going to look at how the exposure and pathway assessments change as you erode your resolution, effectively become more coarse. So we can understand the usefulness of using fine resolution fuels. But so how far out should you go? There's some, and I don't know if Marty Alexander is still on the call, but he might want to chime in. There's been examples of fires that run 20 kilometers in one day. So I think that we could, under very extreme scenarios, you could go out for, like, because for the pathways, we went out 15 kilometers. And so we're kind of looking, all right, like I was primarily basing that on the evacuation work that I'd done, where most fires that prompted evacuations were actually within 10 kilometers of the community. So I said, okay, well, let's go out 15 kilometers. And kind of the idea is if a fire can get to that 15 kilometer buffer, now do they have a way in? But if you were curious about a broader landscape, you absolutely could go out further. The information might get overly muddled. I think you probably reach a point where you don't have a direct pathway out beyond some distance because landscapes are complex and there's water and other things. So there might be some natural scale where it just starts to fall apart because you don't have a trajectory beyond a certain distance. But that would be the only thing that would, if you had an interest in it and you could do it, there's nothing stopping you from doing it at a very large radius.
Okay. And Marty is, when I looked 2 minutes ago, he is still on the call. So, and he says, I think this is in response to your question. He says in 1968, the Lesser Slave Lake fire ran 64 kilometers in a single burning period. Yeah, so that would be an unreal run. And it probably hasn't been duplicated that often, but I'm thinking, under really the one thing that we don't have is certainty around weather and climate change and extremes.
There's nothing in the past that can help us understand that, because there's just enormous uncertainty around what the weather is doing. And like the number of times I've heard experts say, you know, the conditions are unprecedented. We've never seen fire behavior like this. It's, you know, your idea that a fire can only run a certain distance within a time period is reliant on a historical precedent that may no longer exist. And so, you know, those extremes, I think, we don't know if it's pot, and that's a lot of my work has focused on, well, is it possible? Because if it's possible, you need to be concerned about it, because we can't predict if it's going to happen. But if it can happen, then maybe you need to be concerned about it.
Awesome, thanks. Circling back to Michael Curry's second question, will new and updated sources of high resolution land cover data be available soon and updated regularly?
Yeah, yes. One of the benefits of the exposure assessments, and then because they're based on exposure assessments, our pathway assessments, is that they're not tied to the FBP system fuel grids for the country, which depending on which province you're in can have different resolutions. So I've run exposure assessments for the whole country using Landsat data, which has a 30-meter resolution. I'm promising to publish that for about a year, but it'll be out soon, and then we'll make it available. It's freely available data. So I can run an exposure assessment, and I have, for the entire country, and I can run these pathways on every community in the country, and it doesn't take a lot of time to do it. And we can update it regularly as new data comes in. I also validated it at the national scale using the Landsat data against real fires. So it's also been independently validated with actual fires. And there's even better data that's coming. I think that's one thing, that data resolution and our ability to get fine resolution information from satellite imagery and machine learning algorithms that classify it it's just it's incredible how quickly it's changing, and how the available data every year gets better and better. So I'm really encouraged. I think in the years ahead, we'll have even better data, and that's going to make for better quality assessments.
Awesome. Returning to an anonymous attendee's second question. You seem to be focused mainly on Alberta. Have you studied this peril in the rest of the country?
Yeah, absolutely. So yeah, like I have run it for the whole country and validated the exposure assessment for the whole country. And it is being used in BC. And I saw some wonderful results presented recently for the Vernon area, a regional assessment around Vernon. So the BC government has been looking at it as a template, and it has been used in Alberta. There's always a push to use, you know, there's other models out there. People will push to use them. The exposure assessment's relatively new as a strategic planning tool. Like we published it 2 years ago, well, 2019, so 3 years ago. But like I said, in that short 3-year period, it's since been duplicated for Alaska and Portugal, and it's going to continue. So I expect over the years ahead, and there's lots of actually consultants using it, other provinces, Quebec has used it, and I'm working to try to make it accessible. I do workshops and teach people how to do it. I mean, it is really simple. We give out the R code so people can run it. But I think it is taking hold because it is so easy to run. It's computationally, it's very lean. And like I said, you can run it next year and update it at virtually no cost. And the information, I think we've got it to a point where it's, I know maybe you guys can give me feedback on it, but I think it's understandable. When we talk to people in the communities that might not have much of a technical background, they seem to understand intuitively what we're doing. It's not like a big black box simulation that's beyond comprehension. So I think all of those things are going to help. You're going to see more of it in the years ahead for sure.
Cool. And returning to Paul's second question, and this touches on a point you just made. Jen, are some communities using your analysis? Are you aware of some communities that are interested, but something is missing, like funding to move forward?
Yeah, absolutely. There's many communities are using it or have been using it. I do provide, and I have gotten feedback from consultants who are using it. So a lot of communities hire a consultant to go and run an assessment as an input into their community protection plans or wildfire mitigation strategies. And so they will get funding and hire a consultant to do the work. And yeah, I know multiple consultants are supplying these to communities across the country. They contact me sometimes for clarifications on how to do it correctly. They've taken the workshop that I've offered. So I know it's being used across the country. It's being used, like I said, it was being used predominantly by Alberta Wildfire while Neil McLaughlin was there. And now he's gone, he was my co-author on the exposure paper that we published in 2019, or sorry, 2021. So now he's in BC and is promoting it there. He's an employee of the BC government tasked with bringing these tools in. So obviously as a co-author on the paper, he's a strong advocate for this process. So I expect the BC government will be using it more and more. And like I said, I like the analysis is there for every community. So we've already done it for the entire province, and we're doing the fine resolution versions of it for these 5 communities as kind of a pilot study right now in Alberta to learn from the communities so that they can tell us what they need out of these assessments so that we can give it to them, the information to them in a way that's usable. And so we're hoping to learn a lot from them and then make it even more accessible, more broadly.
Awesome. I'm not sure if it's the same anonymous attendee or a different one, so I'm going to assume it's a different one. Have you connected with any Indigenous communities, either to share information or to validate?
It's a great question, and we have identified that as a priority. The communities that we're working with right now, actually, like some of them are regions. So for example, like we're working with Clearwater County, and there are Indigenous communities within Clearwater County. And we're also working with Crow's Nest Pass, so that whole area. So there will be opportunities actually in this current study to share that information, but we are looking for collaborations and partnerships. And I think that's really key for the work that I'm most interested in, is I want to be working closely with communities, hearing from them, and not just hearing from them, but we're trying to do what's called it's an overused term, but we're trying to co-plan with them. We're trying to actually create the decision-making products together, rather than, a researcher goes and makes a map and gives it to the community. So actually, the more diverse the communities, I think the better that we're going to learn from that process. So, yeah.
Thanks. Cheryl, I think your second question, Jen's just answered, at least mostly. So I'm going to skip over your second question, and I'm going to give the last question to Kublashan's second question, because I think that's all we have time for. Jen, if you were asked by the same reviewer to make this one-dimensional model complex, what would be additional dimension or parameters that can be an improvement and not just an addition to uncertainty? I'm thinking of windrows and the information it provides. Thank you.
Yeah, absolutely. So you are getting at sort of what I was alluding to earlier, which is we are looking at the weather component as a separate assessment that you then overlay, right? So we're looking at, okay, the frequency of those days when you can have that extreme weather, and absolutely we are overlaying windroses. And I'm on the fence about that, because actually, like when I did the evacuation study back, years and years ago when I worked at the Canadian Forest Service, one of the most common things that I heard in those evacuation narratives were the winds are never out of the southwest, but that day they were out of the southwest. And so there's a part of me that's skeptical about relying on patterns of wind directions. And yet you can't deny it. There are some regions, maybe because of the orientation of valleys and other things, that you just don't get winds out of some directions. In which case, maybe that's quite reliable. In other cases, if it's possible to have that wind direction, I don't know if you want to ignore that, right? If it is possible, then even if it's less frequent, you might still have it as a concern. But generally, when someone tells me that I should make this more complex, I say no. I don't want to make it more complex. I know that there's like a large camp of people who are very uncomfortable with how simple this is. And there's some cognitive dissonance around accepting that you don't need to make it complex. You don't need to grow 100,000 fires. You could just look at a moving window. But I'm hoping with time, there'll be more acceptance of the simplicity.
Cool. Thank you so much. I think that's all we have time for. I want to thank you again. It's been a fabulous talk. We had great interaction, a lot of terrific questions. I'm sorry we didn't get to all the questions, but we've really enjoyed it. I want to remind everyone that next Friday we will have a talk by the staff of the Northern Hail Project about this year's record-breaking hail season in Alberta. And with that, I'm going to thank you all for attending, and I'm sure we all are grateful to you, Jen, for this your research and this fabulous talk. So thanks very much.
Thanks so much. And yeah, anyone who wants to continue chatting about this stuff, be sure to get in touch with me.
Awesome. Thanks, everybody. Bye-bye. Have a great weekend.